Good, hello, summertime. So you've already seen this, I assume, because I sent an email with this, and I think there's not much new on it. So the first thing on a Monday morning now is statistical methods, and I think most of you took the exam, the first exam by now, and also know your results. Obviously nobody failed, because you also couldn't fail actually on this one, but I think most of you actually get quite a number of points. So you should also be well prepared for what's to come. So this is the general outline. So we are now in the summer term, which is after the spring break. So we're here. And the content of the summer term is a little bit different with respect to the winter term. It would be a little bit stupid if it would just be the content of the winter term again. But it's also different in style, in the sense that the winter term was really kind of a refresher of classical statistics that you can use in any kind of data analysis. Frequentist statistics, as you all know, and this will come up throughout your scientific life. The summer term now is dedicated to stuff that is more relevant, perhaps, for cognitive neuroimaging, and there are two big chunks in this year's summer term. So with the summer term, I play around every year, because the winter term is stuff that everybody needs to know. In the summer term, we can go a little bit more freestyle and do stuff that is of interest also to me. And the winter term is also of interest to me, but in the summer term, I take a little bit more freedom to keep myself entertained with the whole course. And the first part of this year's summer term is dedicated to GLM fMRI data analysis, but a very specific part of that. So I've been teaching GLM fMRI data analysis in the summer term for a long time, and always focusing on a little bit different stuff. And this year I will exclusively focus, except maybe for today's session, on the question of how these p-values that you see for blobs in fMRI data analysis, how these p-values come about. And this will need a little bit of a detour through some probability theory, random field theory, and then some of the idiosyncrasies of GLM fMRI data analysis as it was established in the 90s. And this whole thing will make up our first part of the course. This is of current interest because, like 3 years ago or so, people get crazy a little bit about statistical inference in fMRI data analysis, and currently people, although I would have thought when I entered the field that classical statistics would be dead in fMRI by this point in time, but it's not. So everybody's crazy about it, so we're going to talk about it. So that's the first big chunk. So I allocated 9 weeks to it. Let's see. There is one public holiday. Actually, I won't be here on the 14th, so we have to reschedule that session, but I'll let you know maybe next or the week after how we do that. I mean, we have, of course, the 21st as an option, but I think I don't want to use that, but rather put it on a Saturday or something. Yeah, so that's the first big chunk, and then there's the second chunk, and depending on how fast or slow the first thing goes, the more or the less we will talk about the second one. So the second one is a biophysical modeling approach to fMRI data analysis that uses dynamic models, which means it uses a differential equation framework. And it's called dynamic causal modeling. You might have heard about this as a means to study effective connectivity in the brain. And what we will do there is talk about the underlying model, the idea of using ordinary differential equation systems to model biophysical signals. And then the Bayesian inference procedures that are used to estimate that model. So, of course, the stuff that you heard last term about model formulation, model estimation, model evaluation will come up throughout this course again. Then there will be the second exam, again, like after the winter term, with one date 2 weeks after the end of the term, and the other one then closer to the next winter term. So that's kind of the rough outline. So today I will basically tell you what we're going to talk about and what we're not going to talk about. Questions about this general outline at this point? No. Good. Then another thing has changed a little bit. There are a little bit of new rules because I also, of course, looked into your feedback, and one feedback that came up a lot is it needs to be more interactive, and you want to be more told to work. So I'm happy to provide that. So the way we do it then in the summer term is that there are still these study questions at the end of the handouts, but this term they come without the answers. And then your task is each week to write answers to these study questions. Of course, as you know, by studying the study questions in depth for the exam now, these study questions are just repeats of what is written in the text. So if you read the text, then you know the answers because the answer is in the text. And then we discuss like a couple of them in the beginning of each session. We did the same thing essentially last year, only that I always ask, or last term that I always ask, so what is simple linear regression? And then everybody was like, and so now that you're told to do that, maybe this looks a little bit different. And actually, I have to tick your active participation in the course. So I will use this. So I will have a list of students, and then I will tick you off for your active participation once you answered these questions. And but the thing is that you should write it down. So you should read your answer and not try to bullshit your way through orally when I then ask you. Yeah, so that's kind of the rules. I mean, I find it a little bit condescending and not so nice, but you want it. So I will not do what people tell me to do. Yeah, so so there will be study questions, and I will tell you in the end of each session which study questions you actually should do and which not, because sometimes there will be a little bit more handout or less handout and so on, and we might have discussed more or less. Yeah, questions about this new rule. Yeah.
Are we going to at the end of the term have the correct answers?
Yeah, you will have them, of course, as we will do it for the summer term. There was also some complaint that the exam is too easy and it's not a good way to do it, the way I do it, but I don't think I want to change that now. So you will have the answers to the study questions, of course, in the very end of the term so that you can prepare for the exam again. Other questions? No. Good. Yeah. So so we will talk about the whole thing in terms of neurocognitive methods, of course. So the general outline for neurocognitive methods in the next 2 hours. So starting from 10. So if you have questions how we do neurocognitive methods this term, please postpone them until then. Otherwise, anything? Or can we get started? Yeah, get started. Okay. The handout for today. So I sent you, did everybody get these links? I'm never quite sure, so but I think Google Drive is really clear on that. It says everybody who gets these links can look at the files, but you can download them, right? Mm-hmm. Okay. Because I tried to figure out whether that means that you can download them or not, because there's the option to look at and edit. And I not only want you to look at it, I also want you to download, but I don't want you to edit for the main reason that nobody accidentally deletes everything and then nothing is there anymore. So I will not do stuff on Blackboard this term because it's always kind of an extra step in uploading from where I locally work to that, and don't see much of a benefit in the Blackboard business. Good, so you have the material. So this will evolve. Most of the stuff, the DCM stuff, is actually all there. So I'm going over all these notes because I really want to finish this book this year. So it will become available in steps, but I think if you work on these study questions each week, you will have enough to do for the beginners, so you're not left alone. Of course, you can read about all these things also in the general literature. Good. So then let's get started with content, and especially making clear of what we're going to talk about and what we are not going to talk about. So let's go here. Let's do this. And let's switch here. Let's see. Good. Yes. Good. So, obviously we talked about the GLM in depth in the winter term, and all of you reproduced by now, because you took the exam, what this means. So you all know what this means. And today we're going to talk about how the GLM is applied to fMRI data in a mass univariate fashion. And I will also show you how this is done practically using SPM, also kind of related to what you, of course, do in your neurocognitive methods practical. Now, you have to now in your brain, in your memory system, go back to the time when you studied to the content that was related to fMRI and that you did in the course on fMRI. And the first interactive part of today's session is the question how fMRI data is organized once you have it once you have scanned a participant. So who remembers how data is organized after acquiring the data? Because we want to now analyze the data, and of course it makes sense to first know how the data is actually organized. So please, the master students, how is data organized from the scan? Interactive. You also have to, you cannot say, we need one more interaction, and then when I offer you the possibility for interaction, then you're like, oh, not this interaction didn't mean a different interaction. So come on, try, whatever.
Different voxels depending on which brain area you're in.
Okay, there are voxels. Okay, general, we would, so what we are talking about here is that we scan the whole brain. So of course, sometimes you don't scan the whole brain if you're, for example, interested in visual cortex, but we assume that we scan the whole brain. So you have voxels, which are these three-dimensional entities, like pixels in a photo, and there are voxels. Yes, that's true. Is there anything else than voxels? Or there were other ideas?
They're shuffled.
Shuffled?
Yeah.
What do you mean by shuffled?
I'm trying to remember what slices like shuffled into different sections.
Oh, you mean like that you have interleaved acquisitions? You might also, so that means that whenever you create one of these images, which is called a volume, that you acquire first one slice, then you skip a slice, then you acquire the third slice, and then you go back. But this depends on the sequence you use. You can also do descending or ascending acquisition. The thing is, for these kind of things, you might then want to do slash sum correction or whatever, but the important thing is that you treat one image or volume as a single time point. So you actually ignore the fact that they were acquired at different times and that they were shuffled, as you call it, but you treat one volume or EPI images as one time point. So what is a volume? I'm using, so this is all written up here in this first part, but I want you, we'll do it more kind of informally. So what is a volume? What do I mean when I say volume? I know it was last year. It's quite a long time ago. What's a volume? Please.
It's the unit, right?
A unit in which sense?
Of the voxel. I don't know whether it's the slice itself or the actual one, like the three-dimensional.
Yeah. So when people say we acquired 440 volumes, what do they mean?
440 TRs.
Yeah. Essentially, that's what I meant. So what do you mean by TR?
The sum of all the slices, repetition time.
Yeah. So the important thing is that you need to come back to is that we had that on a slide in the winter term, that the EPI sequences acquire fMRI data in a temporal order, and each of these takes one TR. So what are typical TR values? Yeah, 2 seconds, 1.5 seconds, 3 seconds, something like that. And each TR, so each of these time points, you take a picture, which is called a volume or an EPI image, and it's a 3D picture of the brain. So you have time, and here with the voxels, you also, of course, have space. And these are voxels. And then more on the experimental side. So how long is a participant typically scanned? And what are these units called of how you experimentally acquire data? Runs. And how long is a typical run? We have a few minutes, 10 minutes, 10, 15 minutes, depends a little bit on the style of a study that you're doing and personal preferences. So yeah, I think 10, 15 minutes, 15 minutes, 20 minutes is rather to the long end, 5 minutes is rather to the short end, but you have data acquired in a run of, let's say, 10 minutes. What happens once a run is over?
You're done.
They're done. Yeah, either they're done if you only have one run. Yeah, you have you take a little bit of a break, and then you might start a new run. This always means that if a run is going on, that the scanner is acquiring data. So you hear this EPI noise, then it stops, and then you take a break, and then you might do another couple of runs. And what is this connection or this concatenation of runs? What is that called?
Session.
Exactly. So these terms are, you might think, a little bit random, and they are, in fact, a little bit random. But if you have looked into the COBIDAS report, which is this report by the Committee of the Organization for Human Brain Mapping, there is actually there's a movement a movement towards standardization, and that also means that people kind of use the same language to describe these things, so that you partition a session into runs, and during each run acquire multiple volumes. And so that's kind of the professional language that is used for that, and also to tell other people what you actually did. So you should become acquainted with that language. I would assume that the COBIDAS report is in your neurocognitive methods folders. If it's not, I should definitely put it in there. But also, if you look into the BITS format, which is definitely in there, then you are familiar with this terminology. So that's session runs. During a run, you acquire multiple volumes. Yeah. So what happens during a run?
The participant does some tests.
Mm-hmm. Yeah, and how is this task typically structured? More actually, it's actually more typical of an event-related design these days, unless you're doing vision. But the important thing is that during a run, you do a task, and a task typically has a number of conditions, and these conditions are presented in a number of trials. Exactly. So during a run, you actually, let's now have a run here. You have trials of maybe different conditions, maybe you only have one condition, so that would be a special case, but you have trials that are presented throughout time. So one trial type here with the X might be at these points in time. So here's the start of the run, here's the end of the run, let's say 300 seconds or something, or 600 seconds, that would actually be more the 10-minute run. And then you have another trial type somewhere here, and that's what happens. Yeah. Okay, so I think we have roughly together what we need in terms of how the general data is organized. And the next thing that I want to tell you then is how the GLM is now applied to that data. Or does anyone know? Does anyone know what the mass univariate approach is of the master student? Master students. So do you know how the GLM that we talked about so long in the winter term is applied to fMRI data? After you read all these papers where you saw blobs in schizophrenic patients who got a certain drug or something. So Any suggestions?
I read the script though, so.
That's very good.
Okay.
That's not fair, but it doesn't matter. I mean, it's anyone who didn't read the script, who knew it from other courses, from maybe also my course in the winter term. No. Okay, then Mark, tell us the general idea.
Slide 2, the time series
Mhm.
of each voxel, and then the regression analysis.
Yeah, that's essentially it. So so what we're trying to do now is link this equation here to the fMRI data that we have. So the question is, what is y, what is x, and beta and epsilon in a way follow, but maybe not quite. So first, maybe let's talk about the y. So the y, you remember that were the values of your dependent variable, and you also know that these were n-dimensional vectors. If you are mathematically precise random vectors, and if you observe them, then you have a specific realization. And the question is now, what do these values, so these numbers that are in this y, refer to in terms of fMRI? So what do you want to explain with the GLM? And the answer is as follows. So because of this kind of setup that I explained here for each voxel, so let's say this is a voxel V, you have a time series, and you could of course also plot this, and then have over time values for this voxel, which you might also want to connect if you want when you plot them. So you have TR or time on the x-axis, and you have MRI signal on the y-axis, and you have the time series of a single voxel. And then you have, in this case, NTR, I'm just calling it like that, NTR data points. So your N is the number of TRs you had during a run or a session. So you for everything that we do, actually in the summer term, you can always think in terms of single runs. So NTR would then be the number of volumes that you had in a single run. This voxel you call, let's call that voxel V. So in principle, you have that the observed data you have at voxel V is an NTR dimensional vector. Yeah. So if you were thinking about these Y vectors as column, I'm never sure, as a column of data points, I think they're actually called row vectors if they are a column of data points, then you should continue thinking like that, even if you plot, and we will see that data sometimes arranged like this, which kind of suggests a row of values, then you should always in your head do the transposition from this row of values that you see over time to a column of data points. So essentially you try to model the data from all voxels, which I'm now calling, that's not really nice, let's call them V1, V2, so these are the voxels, Y, V3. You all model them independently if you want, or analyze them independently using the GLM. And because you do that to all voxels, and you do the same thing to all voxels, of course the beta estimates and the error terms might not necessarily be the same for the different voxels, that's the whole point, but the general formula of the GLM applied to the voxel data is the same for all voxels, and because of this, I will not use an index for the Y data. Yeah, so you can, if you want to do something interactive, you can write little GLMs into a box, and then clarify for yourself that you apply a GLM to each of the voxels. The main point is that you do the same thing to all voxels, and this is the reason why I'm omitting an index for the voxel. Yeah, and the data that you then look at is, of course, still univariate. What do we mean by univariate?
One-dimensional.
One-dimensional, yeah. And in this here, it means that each observation, which is given by a specific time point, is still a single number. And this is the case. So this is what we talked about, this GLM form all the time in the winter term. But it's also, or if you want to explain this nomenclature, it's also mass univariate, because you do this univariate analysis for all the voxels in the brain. Yeah, or all the voxels in the data acquisition sequence. Voxels are, of course, not in the brain, but an artifact of your data acquisition. Okay, so that's the data. And then the next question is, what do you now put into the design matrix? And maybe, so I will show you some pictures of what you actually put into the design matrix later, so maybe we don't have to be that specific at this point. So I can just essentially tell you that you're using a multiple linear regression to model the data. So the index now refer to the time point, so to the observation. So this is for one voxel, this is the ith observation, and I runs from 1, which is your first TR, your first volume, to NTR. And then this is modeled using a multiple linear regression model, where you have values of independent variables and their associated beta parameters. And what the independent variables are, that depends on your design. And I will give you a very concrete example once we leave this writing up thing, to show you what these independent variables typically are. The important thing is that these independent variables, so the columns of your design matrix, they now also extend over time. Yeah, so like Y, the row or the column of Y values refers to a time series. So does the row structure of the design matrix. Yeah, so they represent something that evolves over time. And what exactly, I think it's easier to show you visually than to now try to talk about it. Then you have beta parameters, and also the intuition of beta parameters I will tell you in a second. And yeah, you have noise. So I think from this, the most important thing to take away from this here is that the Y is now a voxel time series or voxel time course. That's somehow Brain Voyager terminology, voxel time course. So that means that it's the univariate data of a single voxel over time, voxel time course or voxel time series, and design matrix, beta parameter, and error remain essentially, but we have to talk about them more intuitive in a second. And you do that for each and every voxel, one after the other. Maybe one thing that is important, that also in terms of the indexing between voxels, the design matrix is really the same design matrix at each and every voxel. Yeah? So we will, if I show you how that looks in SPM, you will see a design matrix, and it's really this design matrix that is applied to the data from each and every voxel. Yeah? Good. Okay, so that is kind of a first rough idea about what's going on with the GLM in terms of fMRI. I have a specific example for that I can show you visually, and then we can also do it in SPM. Before we do that, and I think this is a good time to do that before the break, is I went a little bit ahead and jumped from the raw data acquisition to GLM modeling. There is a step in between raw data and GLM modeling. What is that? Pre-processing. And we will not talk about the formal underpinnings of pre-processing because we are not doing that. So in principle, it's interesting in itself, but then it's not statistical modeling, and then I'm also not a pre-processing nerd. There are some people who really like that. I always think it's there. If you pre-process the data a little bit different, something different will come out, but I have to put my attention somewhere, and I put it on the statistical modeling. But of course, you should know what kind of pre-processing you typically do. So let's talk briefly about that, because we will not talk about it again in this course. So what are typical components of pre-processing? Smoothing, that's actually the last thing that people usually do. So what is smoothing and what does it mean?
When you have all the dots, color dots from the, I guess, significant outcomes in the version, I don't know.
No, we are doing pre-processing right now. So so you don't have them yet. So because it's pre-processing, so you smooth. So pre-processing means between raw data and GLM.
I know that.
Okay, so what do you smooth?
Color dots.
No, you don't smooth colored dots. Maybe that's one thing that you should also. I used to do that, but I don't do that anymore. The data are numeric values. So these are things like numbers in a grid. So it helps to think of the data also as in this kind of format, because this is what you think, what you actually see in your computer when you're analyzing the data. So you definitely don't have colored dots. You can visualize these data as colored dots, but what you actually smooth is not colored dots, but these kind of three-dimensional arrays of values. And in which domain do you smooth them? In the time domain or in the spatial domain? Yeah, so I think this is also why I used to call it smoothing, and thought there was something cool in knowing that smoothing is spatial smoothing, but I think it's just stupid not to call it spatial smoothing now. So spatial smoothing, yes, this is done, and typically it's done with Gaussian smoothing kernels of a specific width, and one can talk long about the philosophy behind smoothing, also actually with respect to what we are discussing, so this random field theory-based p-value correction. For now, it's fine to know that smoothing makes the data smoother in space. What other pre-processing steps are there? Slice time correction, which is something that one might want to do or not want to do, as we discussed also in the winter term, so that because it's based on temporal interpolation, it works good if the TRs are not that long. That was actually with respect to the shuffled slices that we talked about earlier. It works good if the TRs are quite short. It doesn't work that good if the TRs are longer, because it's interpolation. If it's longer, then you actually need it. So slice time correction, some people think it's great, some people don't. And then you can have a long discussion whether you want to do it before realignment, after realignment, smoothing, and so on. It's all very interesting. Yes, that's slice time correction. So to make actually each volume represent a single time point, and as we also discussed, it would make much more sense to do the GLM in a slice-based fashion, but nobody does. Anyway, what else is there in pre-processing? realignment. So what is that for?
Is that the one where you set the? I'm not sure if that makes sense, but there was one where you set it to this one area, this one red area, and you make sure that it's all centered.
I think you're talking about some spatial normalization with like AC alignment or something. So why do you do realignment?
Because people move.
Exactly, yeah. So it's the step against movement. So movement artifacts, because your voxel grid in the scanner is fixed, and if people move their head around and out of the voxel grid, then of course specific voxels, which are your data acquisition, not units, but your data acquisition points in space, they refer to different parts of the brain. So you try to minimize that by first of all telling people not to move and fixate them in some way, but you also do realignment also to remove effects of residual motion that maybe just derives from the heartbeat and the pulsation of the brain. Yeah, so that's realignment. You typically do that first with respect to the first image of the first run or to the mean, and then you can have different philosophies and talk a lot about that. And what else? One thing I think we are missing at least. Distortion correction, actually, yeah, you do that even earlier. So this is, or you do it together with realignment. So this is against artifacts of the scanner. So that it distorts your image of the brain. But there's one other thing. Yeah. So what is that? Yeah, depends if you're doing it in brain. Yeah, so in spatial normalization, you typically, so what that means is it's a spatial normalization step so that you warp all the brains into the same stereotactic space, so that brains, so different people have different sized brains. And if you now want to do a group analysis, then you want to overlay the same brain areas of these different people. And to do that, you morph them into or warp them into a common space. So you blow up small brains a little bit, and you shrink big brains a little bit, so that they all have the same size and roughly the same proportion. And this is, you can do that by somehow aligning AC points and so on. That's kind of the old school Brain Voyager approach. Or maybe FreeSurf or whatever. So the typically way that this is done is that you have a template. So you have a template image that is in this standardized space, for example, MNI space. And then you use an image registration algorithm to morph your images to that size. Actually, what there was, so I've been telling people for a long time that, and I always like it when I'm right, I've been telling people a long time that people always somehow do these co-registration steps. So they align T1 images and EPI images, and then they morph the T1 image to the standardized T1 image, and then use these parameters on the EPI to morph them into MNI space. And I always wondered why they make it so complicated and not just morph the EPI image or align the EPI image with the EPI template. And there's recently a paper that actually, I think it's in Frontiers Neuroimaging Methods, that actually is titled, "Do we need anatomical images?" Because they show that you don't gain anything essentially from this co-registration step. So you gain something, like it was always clear, if your EPI resolution is really low for some reason, but with these standard EPI sequences that you use these days, you don't gain anything by using this convoluted way to go over the anatomical image and so on. So just standardize your API images to the MNI API template. Yeah, so these are the pre-processing steps which you should always have in the back of your head. And if you actually, you should have them in the back of your head all the time because you are working on them for your neurocognitive methods project. You will definitely do most of them. So at least realignment, spatial normalization, and spatial smoothing. So you should know what they are. You also have this book by Poldrack and Mumford, which goes more into the details about these pre-processing steps than we do here. You should know that there's a whole computational field that deals with this pre-processing called computational anatomy, and we could actually do the whole course on statistical methods just on this, but we focus on the part that relates maybe more to neurocognitive measurements and neurocognitive theory in terms of data analysis, because this just essentially filters the data in some way that it maybe emphasizes more interesting things, but it doesn't really allow for inferences. What are the interesting things? Okay, so that's pre-processing. We covered that. Have a read of that again, and and know that we will not talk about pre-processing anymore, but we will assume that the data have been pre-processed, and when we acquire our, when we apply our GLM. So let's have a break now, and then get even closer to what we are talking about this summer term. And let's continue at 9, I guess.